In the previous screencast, we discussed kind of all the historical experiments that happened to determine the different parts of an atom. And just as a reminder, the Rutherford model of the atom is where we ended, and that's where we have a tiny, dense, positively charged nucleus with protons, right, and neutrons in the nucleus, and it's surrounded by electrons. Now, this isn't the end of the atom's story. But to really understand kind of the next part, which focuses mostly on electrons and figuring out where those are, we have to understand electromagnetic radiation. Electromagnetic radiation, which is EMR, right? So when we talk about electromagnetic radiation, which is EMR, right, all light is electromagnetic radiation. And basically, we know that EMR, right, or light, travels in waves from a source. When we look at this, this is what we would call the electromagnetic spectrum, and we can see that we have visible light here, and this is the light that we can see. The range of the light goes from red to violet in a rainbow, and that's for us called the visible spectrum. And it's just a tiny portion of the entire electromagnetic spectrum. The only reason we have a special name for the visible part is because our particular anatomy is responsive to those wavelengths of light. There's also ultraviolet light, X-rays, and gamma rays, and then on the other side, infrared, microwaves, and radio frequency. I want to show you kind of two things here. One is wavelength and frequency. We're going to define those on the next page, but I want you to see that they're inverse as wavelength increases, frequency decreases. You have high energy over here and lower energy over here. So X-rays, gamma rays, these are really high energy forms of electromagnetic radiation. And then as we get down here, these are lower energy forms. So let's define wavelength and frequency. So wavelength, when we look at this, a lot of times is represented with the Greek letter lambda, which you can see here, it's kind of this wavy line. And that is just the distance between, missed a letter there, adjacent crests or peaks in a wave, right? And so when we talk about crests here, these little peaks. We can also talk about troughs here, which are where it bottoms out there. And when we talk about wavelength, it's this length here. It's normally measured in some sort of unit of distance, meters, centimeters, nanometers. Then we can also talk about frequency, which is the Greek letter nu. It's this V-looking letter. And that's the number of crests that pass a point. And then the third kind of thing that we talk about with waves is amplitude, and that's the height of the crest with respect to the center of the wave. I forgot to tell you the units of frequency up here. The units of frequency up here are sometimes a second to the -1, which is the same thing as saying 1/seconds, or hertz, which is abbreviated HZ. Now, all electromagnetic radiation travels at the speed of light. So that's something to be aware of. Which is 2.998 times 10 to the 8 meters per second, and that equals c. And that c is just the abbreviation of the speed of light. This is the same c that you see in the really famous equation, E equals mc squared. Okay. I love visuals, and so I wanted to relate the wavelength to what we see in the visible spectrum. And so what you can see here, right, is that violet has a shorter wavelength, and then as the wavelength gets longer, red has the longest wavelength, and you can see where the colors change, or how we see the light or colors change. You can also see we've got some approximate numbers here. Please do not memorize these, but I did want you to see the visual where the reason we see different colors is because we have different wavelengths. Now, before experiments in the 20th century, matter and light were viewed completely separately. So matter was, everybody thought it was composed of particles and had mass, okay? And then light, completely separately, everybody said, hey, look, that moves as a wave, so it's wave energy, right? And it has no mass. Okay. Well, people performed experiments, and those specific experiments are sort of outside the scope of this course. But what they figured out is that, and this was really wild at the time, is that light has properties of both a wave and a particle. Okay. And so when we talk about this and these particles, a photon is the particle of light that we talk about. And so this whole idea is called wave-particle duality, right? So the light functions both as a wave and a particle, with photons being those particles of light. Now that we've talked about all this, if there was a little stop and start there, you didn't miss anything. I had to stop the screencast for a moment. So we've been talking about light, right? And there was a phenomenon that happened where a guy named Niels Bohr studied. And basically, if hydrogen gas is placed in an evacuated tube and an electric current is passed through the gas, light is emitted. Now, here was the wild thing. It wasn't all the wavelengths of light, so it didn't look like a rainbow. It was a specific wavelength, right? And this is called an emission spectrum, and it was just one color. And so what Niels Bohr did is he studied helium. And he really wanted to explain why you only saw this one color, this one line, when in the helium emission spectrum. So his hypothesis was that electrons are in different energy levels. So let's put some words to that. Niels Bohr studied the emission spectra of helium, right? And it gave a one-line color, right? And so he hypothesized that the reason it did this is because the electrons, which I'm going to abbreviate as E minus, are in discrete, which just means individual, energy levels. And there's, of course, a picture of Niels Bohr. So we've got these electrons, they're in the discrete energy levels, and we can kind of view these energy levels as steps on a staircase, okay? And so you start out here at the bottom, and this is the nucleus, right? And the nucleus is here, and so this first energy level is given this kind of abbreviation or symbol N equals 1, right? So the N's here are just the energy levels. So this N equals 1, this guy is closest to the nucleus. And here, those electrons are the lowest or lower, let's say lower, in energy compared to electrons in all the other levels, right? N equals 2, N equals 3, N equals 4, N equals 5. And then the farther you get away from that nucleus, you end up with higher energy. Right? So there's higher energy the farther that you get away. Now, the electrons only live in these specific shells, and so the reason it's described as a staircase is because just like you can only go up like one step, you can't go up a half a step. The electrons aren't floating here kind of in the middle of the steps. So it's either one or the other. This is referred to as the quantization of energy. And then the levels, a lot of times are related, are called N, but they're also known as shells. So sometimes you'll hear people talk about the different levels that electrons are in as shells. And that's what you see there. And the shells, this N shell, it's is what they're referring to a lot of times. Now, although Bohr's concept of the principal energy levels is still valid, restriction of electrons to the fixed shells, or sometimes called orbitals, is too rigid. We now do not believe that electrons orbit the nucleus like planets around a sun, okay? What we do believe is that electrons are moving very rapidly, and spread out the charge into a cloud, right? And so we now refer to the probability of finding an electron in a region of space, and that region of space is called an atomic orbital.